So good afternoon. I'll try to be quick, as people are probably thirsty for beer or wine. What I want to talk about is some efforts that we're doing now at Ocean Networks Canada in the area of early warning for earthquakes. But before I get there, you may think, what the hell is an ocean network got to do with early earthquake warning? Well, I'm going to spend 4 slides on that. So Ocean Networks Canada is an organization, a not-for-profit, that's located at the University of Victoria in British Columbia. And we are the operators of the so far largest underwater networks to study the oceans. And so we have over 200 instruments that are installed on the water, connected via cable, submarine telecom cable, back to shore. And they can provide us with data about the environments on the seabed, under the seabed, and in the water column back to shore. It so happens that we also have on these systems, both the Neptune observatory that you see here and the Venus one over there, we do have also seismometers. And those seismometer data, mostly broadband systems, is going straight to IRIS, and within a few seconds it's available there. We also happen to have a small observatory now in the Arctic. This one doesn't have a seismometer though. But the themes that we're exploring through Ocean Networks Canada are related to those 4 major aspects of science. The one that is particularly relevant for this audience today is the seafloor in motion, obviously. We're an organization that's not for profit, yet we need money. The government is insisting that we also find our own money. So we have an innovation center, as we call it, that is supposed to commercialize technology and expertise. And I just have to mention them because it's an introduction to the next slide. We got recently some money to develop a smart oceans system that is supposed to, in the case of the province of British Columbia, deliver what they call a world-class ocean area management system that helps tanker traffic and other assets, but also address priorities regarding geohazards. So in this context, we're planning to expand on Neptune and Venus and have more observatories along the coastline, you know, this blank spot between Alaska and Washington. We are going to be installing more seismic sensors as well as other sensors that will provide some facility to aid navigation, detect ships, but also calculate sea state and provide a baseline on the health of the ocean. Among the geohazard detection projects that we have, we want to focus on 2 essential ones. One is the tsunami detection and notification, and the other one is earthquake detection and notification. As I mentioned before, Ocean Networks Canada is dealing with sensors that are mostly located underwater, but nothing prevents us from having sensor above water on land as well. We're just dealing with sensors that are connected to a network. The map that you've seen before that shows our underwater network is really just the extension of the internet underwater. And that was our theme. So basically, if we can do it underwater, we can also do it on land. So that said, we've got a data management system that we call Oceans 2.0 that collects the data from all these sensors and makes it available to our users, to our science users. What we want to do next is do a little more, provide out of the data management the calculation of localized forecasts. In the case of the ocean, it would be sea state and health of the ocean parameters to construct a baseline. But more importantly for this particular audience is the event detection that would happen under this WARN project that I quote here, WARN standing for Web-Enabled Awareness Research Network, which is a fancy title that pleased our funders somehow, because they gave us the money to do it. The WARN output, which I'm going to coming back to in a second, is feeding into localized forecasts, both for tsunami impacts, basically calculating at every point on the coast, or at least some selected points of the coast, what a particular wave height could be at the height of, or when the tsunami will hit. But at the same time, we also want to feed into earthquake impact models the detections that we made of an incoming earthquake. These earthquake impact models would, for example, calculate the potential impact on buildings in urban centers and help later on direct the emergency response crews to the right places. At the same time, of course, the event detection for earthquake can also directly feed computers with information at our stakeholders' locations, and I'm coming back to that. So summary, we get as input the data from accelerometers, pressure sensors, radars that will feed into our warn system and produce as an output for earthquakes, time of arrival, latitude, longitude, magnitude, some understanding of the confidence. For tsunami, essentially the same thing, times of arrival, directions, height, position, and confidence. What we want to do in terms of earthquakes is implement a system similar to what is being done here. You guys have probably a good 2 years of, you're 2 years ahead of us, and Japan is countless years ahead of us in this story, obviously. But what we want is to integrate also with the impact prediction and disaster response models, as I mentioned in the previous slide. We are trying to take advantage of new sensors that are hopefully inexpensive to detect, and dense enough, obviously, to detect, analyze the P waves in situ. Currently, we're using a University of British Columbia design, but of course, there's many, many different sensors. And as the previous speaker let us know, we could even drop hundreds of cell phones all over the map and hope that we also get some data from those. What we want to basically do is also take advantage not only of the data management system that we have, but also of the assets that we have underwater to supplement our sensor network with more accelerometers that we will place underwater as well to, as in the case in this map, basically create a lens with our sensors that will allow us to image faults underwater from two sides, from the land-based as well as from the ocean side. So if you look at the map there, the green dots on the map are two accelerometers of the types I described before, this UBC development, that are already installed underwater. And the red pins on land are sensors that we want to install initially just for the test purposes on land. What the funders gave us, and what I managed to sell them with a fancy title for the proposal, is really money to develop a software system and a software infrastructure that will take the data from the sensors and produce the detected signal that will then feed into the client side. So again, we have sensors and P-wave detection that hopefully occur in a co-located environment, whether it's land-based or underwater, or it's close as possible to the sensor. Then at our data center at OceanWorks Canada, the warn system will provide event correlation, so basically assembling the detections from individual sensors and deciding whether it's a real event or not, and hopefully not missing any. And then this event, once detected, will feed into a notification system that will speak the CAP protocol and then make the data available to our subscribers, our clients. What are our limitations? Obviously, it's going to be a regional system. We don't have at this point the funds to install more sensors, but we have another phase of this program which will have money to install more. Plus also we hope that we'll be able to reuse and connect to the data coming from the sensors from other organizations that have already been installed to basically improve on the detectability of the events that could occur in our region. It obviously is not designed for something you're sitting on. I mentioned that, but initially it's not meant for the public. Obviously there's liability issues here, but we want to go with, just like what's happening here in California, with a few selected facility or large facility operators from trains and pipeline operators, hospitals, with the ability to have them test the system and implement their own client side. The advantages that we represent, the software system we're trying to put together is going to be sensor independent. It's going to be designed to be tolerant of unavailable sensors We'll have underwater sensors, but of course this is because of our geography and where we're expecting most of our earthquakes. It's relying on the work that's been done elsewhere, and it's basically just with the advice of my co-author here, Andreas Rosenberger, basically re-implemented or implemented in our environment. It's going to be a client-server model, as I mentioned a few times. There's a subscription-based system. Our server, that is us, will provide the alerts that consist of origin, time, epicenter, location, magnitude estimates every second during the event, as long as it's confirmed by 3 or more sensors. And then on the other side, at our stakeholders, basically they'll have a software system located on some computers of their choice that will just be listening for warnings from us. And once the CAP package comes over, they decrypt it, calculate distance, impact time, using modified Mercalli intensity. How we've implemented it, we have sensors that have PTP synchronized clocks. They send the detection system sends 2 types of messages from them. The 1 Hertz heartbeat that recalculates intensity every second, even if it's noise, but it's useful to have as a heartbeat. The P-wave detection with time of arrival, then of course. And then on the server side, on our data center, we'll listen to the P-wave detections, calculate epicenter using grid search when we have at least 3 or more detections in the same time window. And then we revise this intensity using well-known methods that have been talked about in this conference many times, basically, well, all the time. And once we have a positive detection, then we can send the alert out. On our client side, which if there are IT people in the room here, it's actually the reverse. We assume that the clients here are meaning stakeholders, but they will run a server that will listen to incoming calls from us. They'll be listening to the notifications. It calculates the distance from the epicenter. I've already mentioned that. Time of arrival, revise intensity, and implements the decision and actions according to the pre-established scenarios of these people. And I'm not going to cite the examples that have been already mentioned many times around in this conference. So nothing very specific here. Again, I repeat, the funding that we've got was to set up a software system. It's not to focus too much on sensors. It's not to focus too much on the client applications. It's a research system that we hope will be able to be reused in an operational application in the next 2 or 3 years. And I believe this is it. Thank you.
Any questions? No? Okay, thank you.